I am Radhakrishna Prabhu. I am from Robert Gordon University. I'm an academic in School of Engineering. So we are from Northeast part of Scotland, and we are glad to be part of MDMC, and again happy to be joining the exciting work what is being done in other major universities. My presentation, I will start with general introduction on the university and some other courses in engineering. Then I will move on to some manufacturing capabilities in RGU and some characterization and some applications. So from RGU's perspective, RGU is one of the youngest universities, maybe post-92 universities, and which has quite strong interest in excelling teaching and research. So from teaching perspective, which is related to medical or biomedical side, you have postgraduate courses in biomedical technology, again, undergraduate courses in biomedical technology and applied medical sciences. Then we have recently started a graduate apprentice course related to manufacturing. So we are very much relevant to MDMC from teaching side. Again, from research side, we have strong medical related research, and we have strong interaction with local health board, especially NHS Grampian. So we have colleagues working from School of Engineering, School of Life Sciences, Computing, as well as from Health Sciences with NHS Grampian. Now, moving on to some of the manufacturing facilities. This is, I've picked up some samples beyond School of Engineering. So broadly speaking, we have many 3D printing facilities in RGU. So one of the examples is Intemis FunMat Pro. It's a large format industrial printer, and it is high precision and very accurate printing machine. On the extrusion type filament manufacturing, we have few facilities for developing filaments to few microns or millimeter diameter filaments. And again, fused deposition modeling, we have three prototyping machines throughout the university. So they can be used for different type of plastic materials. Looking at 3D printing, again, we have plenty of 3D printing machines all over the university. In engineering, we have, I think, around 10 machines, and we can do small type of works with this. Looking at the metal 3D printing machines, we have an EOS M100 machine, which is very good for rapid prototyping. And again, it's good for medical applications. I think it can take materials like cobalt chrome, stainless steel, as well as titanium, which is relevant for medical applications. Again, from forming machine, we have a forming machine which can be used for making coverings. On to digital manufacturing. Again, we have plenty of CNC type machines, laser cutting and laser welding machines, and they are widely used in other schools than engineering. So from laser, again, we have a big sintering machine which can be used for 3D manufacturing, 3D printing. And on the picture you see a unique machine, XYZ, vertical machine center, which can be used for fabrication or manufacturing 3D devices. And I will slowly move on to next facilities, which are relevant to me. Now, we have been working in School of Engineering. We have been working on glass development. So we have a range of high temperature furnaces, and with temperatures going around 1600. So we have been working on functionalized glass and glass ingots for developing nanomaterials or nanoparticles or optical fibers. So these nanoparticles, as you can see, yeah, this glass can be manufactured with rare earth doping, and we have generated some multicolored glasses under fluorescence imaging. You can see green, red, or yellowish color. So we have expertise in developing glass material and nanoparticles. So on the left side, you can see nanoparticles under microscopic illumination or fluorescent imaging. So we have developed nano and microparticles using rare earth doped glasses. Onto some characterization. So in line with the spectroscopic approaches, like we have absorption spectroscopy for characterizing transparency of the materials, and fluorescence spectroscopy for, again, characterizing fluorescent properties of the material. And we have machines like PerkinElmer and Edinburgh instruments in our labs. And they have wide range of wavelength, starting from UV to near infrared. And again, the Edinburgh instrument is a modular instrument and which is very flexible. And especially this machine can take laser input from an Nd:YAG Oppo laser for laser excited fluorescent measurements. Again, we have a Raman spectroscope from Avalon for characterizing samples, glass samples. Now again, on the surface analysis, we have X-ray based machines. So XPS is one of the systems we have in our labs. So this is from Kratos, which is good for surface characterization and very relevant from medical applications perspective. Again, for the surfaces, we have a contact angle measuring system, and typical example is shown on the right side. So we develop nanowires on medical devices or medical surfaces, and to tune the surface properties and study the surface properties, we can use this water contact angle measurement system. So we can tailor the surface properties from hydrophobic to hydrophilic or hydrophilic to hydrophobic through chemical or non-chemical approaches. Again, one or two applications that we have been working on. Like other partners have indicated, we also have some interest or expertise in microfluidic chips. So one of the chips we have developed here on the right side shows this was part of a cancer POC, point of care type cancer detection system. So the overall chip is a size of a fingernail, which is probably 4 millimeter by 4 millimeter and 1 millimeter size. So it integrates sensors inside the microfluidic channels. Both optical as well as electrochemical sensors have been integrated into these channels. And we have done a lot of, and we have, as a group in School of Engineering, we have a strong expertise on CFD modeling, computational fluid dynamics modeling. And the group has been working more than 15 to 16 years now. And most recently, they have been working on aerosol transport. And they have been studying the behavior using ANSYS software. Again, we have other softwares like MATLAB and COMSOL for microfluidic devices. And we have used glass and polymer materials for making microfluidic devices. Especially my background is biosensors and instrumentation. So we have expertise on packaging whole device and the instrumentation for point of care applications. So on the last slide, again, we have been working on optical fiber sensors. So as you know, optical fiber sensor is very flexible. Optical fibers are very flexible, and they range, the diameter of these fibers can range from 100 to maybe 10 microns in diameter, and they can be used in a variety of applications or biomedical applications. And it can be used for delivery of laser pulses inside the body, or for endoscopic applications like imaging and for sensing. So we have used uh, step index fibers, hollow core fibers, photonic crystal fibers, or integrated both hollow core PCF fibers for various medical applications, mainly on the sensing side. So for one of the simplest fiber sensors is based on fiber Bragg grating, where grating can be inscribed into core part of the fiber and can be used for sensing temperature, strain, or any chemical, specific chemical composition in the blood or inside the body. So in addition, we have a strong research group working in computing in collaboration with Health Sciences School on wearable sensors. They are very strong on data analytic side. So they work on developing the wearable sensors and data analysis. So thank you very much. That's all from me.
Prabhu, thanks